I've always admired games that do interesting things with replay mechanics. I think fondly back at my days playing Halo 3 and messing around in the theatre mode, or making sweet action movies from all the sick stunts I pulled off in the director mode for Driver 3. But, even more recently, one of the most impressive uses of a replay system to me is the one in the Forza series. I adore that if you screw up your perfect line, you can just rewind the race there and then. There's no doubt about it, replay systems are just cool. So, given that I'm working on a competitive driving game in my spare time, where cool stunts and sick jumps might happen, as well as the inevitable requirement to eventually have to market my game and produce a trailer for it, it just made sense that I can kill two birds with one stone and introduce a replay system into the game for players, but mostly myself, to use. Hi there, I'm Matt, and welcome to Game Dev Guide. In today's episode, we're going to look at how we can produce our own replay system in Unity. We're going to look at how to set up a basic system that can capture the state of various objects in our scene and then recreate their state via playback based on what was captured. We're then going to look at how we can build tools for the player to scrub back and forth through this data we've captured in-game, as well as build some additional tools for basic cinematic capture. Finally, we're going to look at how we can export the replay data and reload it again for sharing, or more importantly, debugging. So, by the end of this video, you should have a pretty comprehensive understanding of how to capture and replay data in your game, as well as a basic understanding of how to build capture tooling for your project. Before we get started though, I'd like to take a minute to thank the sponsor of this video, Bezier Sidekick. Bezier Sidekick is your programming partner for Unity that enables you to focus on the creative and complex parts of game development by quickly handling all the repetitive and boilerplate aspects for you. For aspiring and improving game devs, it's a great learning assistant for the technical aspects of the game development journey and will augment your development speed. Sidekick can rapidly write and debug code, answer your creative and technical questions, and update your scene to fit your project's wants and needs, all based off of real-time context of your project, the codebase, asset folder, scene graph, and more, making it quick and easy to implement game mechanics. These suggestions are powered by a deep knowledge of Unity best practices and documentation. Your information stays between you and Sidekick, your project integrity and data privacy are totally secure, so your project stays yours, 100%. Check it out at www.bezier.com/sidekick or by clicking the link in the description down below. Now, let's go ahead and get started building out our replay system. I have a little playground scene here with a vehicle that you can drive around. There's a few jumps that you can make and a few different prop objects that you can smash into. Some of them even break up into pieces when you hit them. We have about 30 seconds on the clock here before the session ends, and essentially, I want to be able to record everything that happens from the moment the clock starts until the moment it stops, and then be able to play it back smoothly via this replay button here. The plan then is to write a data container that requests a snapshot of the game state at a given interval. We should then be able to move through each snapshot in the container and restore it at the same given interval to create playback. So, let's start by creating a script to manage our replay mechanics and hold our data object. We'll create a new mono behavior called Replay Manager and set it up as a singleton instance. We'll also create a game object in our scene and attach our script. This is going to be where we record the state of our game into our data container, and I'm going to create a scriptable object called Replay Container where our data will live. Theoretically, this data could be in a struct or something, or live directly inside of the mono behavior, but I find making an actual object to hold the replay data more useful for visualizing and debugging, and we could have more of them later if we wanted. Okay, so we have our manager and our data object. We're ready to start setting up our snapshotting system. It would be pretty wasteful to serialize the state of absolutely everything in our scene, especially if most objects remain static and don't really change state much between frames. So we'll only want to update objects if they've actually changed between frames, so we'll design this in a way that leaves it up to our objects to decide when and what to save. Our data container then won't really need any understanding of what's in the scene, but instead should just store a snapshot of the data each object cares about. What we can do is use an interface to have all of our objects that we want to save register themselves to our manager on load. Our manager can then call a shared method on all of those objects, and we can use this to store the data that we want. Let's create a new interface called iReplayObject, and then add the SaveSnapshot and LoadSnapshot methods. In our replay manager, let's then create a list of replay objects. So, Now we can take the objects that we want to store data for and have them implement our interface. Let's start with the vehicle controller here. I'll add the iReplayObject interface and implement the two methods. We'll also call the register method on the replay manager to register our object and add it to the list. Let's tell our system to snapshot our object data every few frames. We'll need to create some kind of container class to hold all of our object snapshots each time we capture them. So let's write a struct that can act as our data group for any specific snapshot. In this struct, we'll have an identifier for the current frame time and create a dictionary of objects that will reference via a string ID, as this will enable each snapshot to be more explicit. For instance, if an object state is idle over multiple frames, we don't really need to capture or restore that data until it's changed. So we can use IDs to manage the restoration of objects we care about and ignore the ones that we don't. We'll go into this in a little bit more detail later. We'll create a constructor for this struct that will take in our current frame, and we'll also add a new method for adding a snapshot to our dictionary. In our scriptable object, we'll add a list of structs and some code to initialize our list. We'll also add methods for adding a new snapshot and fetching a snapshot. Now, we're almost ready to start storing our data. We just need to tell our replay manager to capture it. So, let's create a method for calculating how and when to store a new snapshot. Our replay manager should have three states: idle, recording, and replaying. So let's set up an enum for that so we can tell our manager what state it's in and what it should be doing during gameplay. We'll also add some methods for switching the current state. Now, we could capture all of the frames on every update, but that could potentially be extremely expensive to do, especially if we're targeting higher frame rates. So there's a balance we'll want to strike between performance and precision for the replay, and your mileage will vary here, so for some flexibility and tuning of the replay capture, let's add a variable for the time between frames to capture a new snapshot, and a running total of the current delta between frames so we know when to capture a snapshot. For now, I'll set it to capture every 0.03 seconds. We'll also go through and tell our gameplay manager to start recording the session when we start, and stop recording when the session time is over. Then in our replay manager, we'll calculate the current frames and work out if we need to take a new snapshot. If we do, we'll call the snapshot method, where we create a new snapshot data struct and pass in our objects. So, we're almost ready to go, but we need to tell our replay system what to save. So, I'll create a new class called snapshot_info and a derived class called vehicle_snapshot_info. In our vehicle snapshot data, we can write fields for all of the properties we'd like to snapshot. In the case of my vehicle controller, I basically just want to snapshot its current rigid body state and its transform state, plus any inputs that exist. We'll ensure that every piece of info has an ID for who it belongs to, and then I'll update the interface and all of our other objects to use this data type. Finally, we can take our snapshot info and use the ID from the info class to register it in our dictionary and save the object. So, to summarize, when we call takeSnapshot in our replay manager, we create a new piece of snapshot data where we iterate over our registered objects and request the data that we should store from each object, which right now is just our vehicle controller, where we store our current position, rotation, and player input. Then, when all of those objects have been processed, we add that snapshot to our replay container, and so each entry in our scriptable object represents a snapshot of a given frame. That snapshot contains a list of game objects and the data they care about. If we run through a session quickly, when we get to the end, we should now have a data asset that stored all of these variables from our vehicle at various points throughout the run. We've successfully recorded a replay of our vehicle. All we need to do now is add support to play it back. In our replay manager, we'll pay attention to the state that we're in and choose whether to send data to our container object or fetch data from it. And in our snapshot loading method, we'll try and get the current snapshot and go over our replay objects, requesting data for each one. If we get some back, we'll simply pass that to our object to load it. Over in the vehicle script, we know that the data returned is for our object, so we can convert it to our info class for our vehicle and set the data appropriately. After loading the data from our initial snapshot, we'll increase the current index and check if another snapshot is available, marking the timestamp that the next snapshot represents. We'll use this data to tell our replay system whether we should try and load the next snapshot or not. Essentially, we're checking if the current delta of frames matches or exceeds the queued snapshot, and if it does, we'll load it. This should help us keep the replay mostly in sync between variable frame times. The idea behind using a dictionary is that we can very quickly grab a snapshot based on its object ID. But because we're trying to fetch data from a dictionary, and dictionaries don't serialize in Unity, we'll lose all the stored data once we exit play mode. So, we'll introduce a list to store data for debugging. When we first request data from our dictionary, if it's null, we'll rebuild it. Again, this is mostly just to support playback between play mode sessions for debugging, so it is a little bit pointless, but it's valuable for testing and obviously for this video. At this point, we should now be able to record an initial dataset, stop playing, disable the recording feature, and then when we go back into play mode, our vehicle should start its playback. Pretty neat. We've now got a very, very basic system for recording data. Depending on the complexity of your project, it's worth tweaking the target frame time a bit for more recording data. Obviously, the more frequently we record a snapshot, the more accurate our playback will be, but as this scales and as we record more objects, the more demanding this may become. One of the things that you might notice is that it appears as though tracking the vehicle controller is enough. Our physics objects all behave the way that we'd expect when we're playing back our recording. And again, depending on the demands of the game, this might be sufficient. But let's take a look at what happens when we have closer control of the playback. Let's add a quick system that will let us scrub through the replay in the inspector here and each snapshot individually. With a custom editor, I can calculate the maximum snapshots captured and build a little slider to allow me to scrub through them. I'll then update the replay manager to support scrubbing through by only updating our index when we're in playback mode. If we're in scrub mode, we'll just continually set our objects into that position. As you can see, while in playback mode, it appears as though our simulation is accurate. As soon as we start scrubbing and moving it back and forth between frames though, the simulation is broken and our physics objects are completely out of sync from our vehicle. This makes sense, obviously, as we've only recorded the vehicle's data, and the rest of the physics engine is just doing its thing. But if we want accurate playback for our entire scene, then we'll need to add our physics objects into the replay system as well. Thankfully, we've already done most of the work, and now it's basically as simple as implementing our interface and then registering all of these objects with our replay manager. The only main difference here is that sometimes I'll have multiple instances of a prop in the scene with the same name, so we can't rely on using the name as our ID. Instead, I'll assign a unique GUID to each prop when it's spawned in the scene. Now, as we scrub through our physics objects, we're able to rewind and reset. However, we've got a little bit of extra work to do for the destructible pieces here. These pieces basically work by detecting if the player interacts with it and then switches the active mesh to a set of pre-cut objects where their individual physics then take over. So in order to track them, we need to evaluate and record the given state of the main object and the individual pieces. In our snapshot data, we'll check if the object has been flagged as destroyed, and in this instance, we'll track and snapshot all of the sub-object info. When restoring a snapshot, we'll check over these three various states and then handle the snapshot info accordingly. With that, we now have a pretty robust replay system that we can navigate through in the inspector and step through any specific frame. Standard physics objects react to the frames, as do destructible sub-objects. I really enjoy being able to scrub through and see the destruction frame by frame here. It's really neat. As I'm sure you can imagine, this is not only cool for gameplay purposes, but it's incredibly useful for both debugging and for gameplay capture, as we can scrub through the action frame by frame and get cool screenshots for any moment through the session. So, why don't we implement a quick UI and some basic logic for gameplay capture so that we can scrub through replays in a build rather than just here in the editor. I've already covered the basics of UITK in a previous video, so let me just give you an overview of the UI document I've put together for our replay here. Essentially, we'll add a replay element to our UI and put together a progress bar at the bottom with a fill element. We can then map the scale value on our fill element to this progress value in our replay manager. And during playback, our progress bar scales to represent the current frame of our replay. Perfect. As a nice little extra, I've gone ahead and added a toggle to decouple the camera. This toggle disables our vehicle camera and enables a different scene camera that we can then control. On this camera, I have some special input actions and a script to enable me to move it around and position it in the scene. I can also pause the playback, as well as scrub it back and forth using some keys on my keyboard. And just like that, we've got a cool little capture tool ready to go. At this point, I'm pretty satisfied with what we've built. We've got a pretty robust replay system that allows us to play back our sessions and scrub through it, as well as a neat little cinematic camera tool for capturing footage. However, if I don't have the time to do the capture immediately, we're going to need some way to store one of the replays we like so that we can use it for capture later. Additionally, I know that people will be playing the game and may come across bugs or have issues. So I figured it could be important to have a way for me to review their gameplay sessions without them necessarily having to have been recording their screen at the time. By exporting their replay data, I can load the capture of their session on my own build and review what happens. The video is super lengthy at this point, so I'm not going to go into too much detail on the specifics of serialization, but essentially we can convert our data inside of our scriptable object into JSON, write it to a file, and then do the opposite to load the JSON back into the level as replay data. So to start with, we'll add the hidden Newtonsoft JSON package in the package manager and import it so that we can take advantage of some of its advanced features. Then we simply go through and add JSON parsing to all of the classes we created. We can then use the JSON convert feature and write it all to a JSON string, which we can then write to a file on our system using the file writer. I've hooked this feature up to this button in the inspector, and as you can see, we've now written out all the data from the scriptable object into a file that can now be viewed and shared. To load this then, all we have to do is retrace our steps backwards by reading the string file in Unity and converting the JSON strings back into their original class, and then place all of that data back into the replay container. And as you can see, we can now go from having a fully empty dataset to loading from our JSON and playing back the replay we captured earlier. I'm using this exact same replay system in Cabs of Chaos, where a typical game session runs for around 10 minutes. And as you can see here, we can easily scrub through a full session and save it directly to our file. For that game though, I wanted a more seamless save-load experience with reasonable file sizes, so I made some optimizations. This included selecting specific data to save and truncating certain values to keep things efficient. I also chose to write the replay data on a separate thread, building the JSON frame by frame. This way there's almost no performance impact while saving because the JSON is already pre-built and ready to go. The key takeaway is that I'm using the same foundational logic I'm showing in this video. While you may need to adjust it and make optimizations for your own project, my implementation in Cabs of Chaos should demonstrate that it can scale to different use cases effectively. And so that's about it for today's video. Like everything I share here, this is just a starting point and a lot of it depends on the unique demands of your project. This approach has worked well for me and my game, so I thought it might be helpful for some of you too. So I'd be interested to know if this has helped you at all, or perhaps if there are any alternative methods you might be using that other folks might also find useful. Either way, be sure to leave a comment down below and let me know your thoughts. If you've enjoyed the video, don't forget to hit the like button, and if you're new to the channel, please do consider subscribing as you'll be notified when new videos go live. If you'd like to see more from me first though, feel free to check out one of the other videos on screen now. As always, thank you very much for watching, and I will see you again next time.